Hello everyone, good evening, welcome. So today's topic is modulus function, regarding which questions are repeatedly asked, and uh, there are some standard results and concepts around modulus which we need to know, and I would like to showcase all the different kind of concepts and the kind of questions that can be asked, have been asked. So all the concepts will be able to understand through the questions that I have brought today. Let's start. So first question, how many pairs x and y satisfy the equations given below? And you can see there are two equations. X plus mod y is 8 and mod x plus y is 6. Now first of all, what is modulus function? The modulus function takes any input and gives out the output as the magnitude of the input. So mod of 10 is 10, whereas mod of minus 10 is also 10, right? So mathematically, modulus function is defined as mod x equals x when x is positive and mod x equals negative of x when x is negative. That is the standard mathematical definition of fx. So in this question, for example, we can see that the mod terms are involved in the variables. The standard way to deal with any such question of modulus is that you break down the each term as per whether the input is positive or negative. So here we see two kind of equations which I won't say are linear equations, although they are, but they are not in the sense that the input to the terms are modulus functions. So we need to break apart the modulus and then they become linear equations. So the equations you can say are convertible to linear equations as per the different range of the values of the input. So if x, for example, for the first equation where it says x plus mod y equals 8. So if mod y is y, if y is positive, then mod y is y, and if mod y is negative, if y is negative, then mod of y is minus of y, right? So uh, can I say that y is positive or negative, x is positive or negative? They create four different combinations of x and y, the sign of x and y basically. So the equations will become linear equations, but they will become linear equations in four different combinations of the values of x and y. So we need to take four cases. Case one, x and y both are positive. X is positive, y is positive. Then what do the equations become? First equation becomes x plus y equals 8, and the second equation becomes x plus y equals 6. Now these equations don't have any solution because they are inconsistent, right? X plus y cannot be 8 and 6 both at the same time, right? So there is no solution from the first case. Second case, if x and y both are negative, so then mod x will be minus x and mod y will also be minus y, right? In the first case, when x and y both are positive, then we applied x and mod x is also x, mod y is also y, right? So now what do we get? We get x minus y is 8 from the first equation, and from the second one we get minus x plus y is 6, which is as good as saying that x minus y is minus 6. Again, these equations are inconsistent. X minus y cannot be 8 and minus 6 both at the same time, right? So hopefully there is some solution to be obtained from the other cases. If x is positive, y is negative. Let's see what happens. If x is positive, mod x is x, but y is negative, so mod of y is minus of y. So from the first one, we get x and minus of y is 8, and x plus y, since mod x is the same as x plus y is 6. Yes, these equations can be solved, first and second. So we get 2x is 14 or x is 7. X is 7 and then y is x minus 8 from the first equation, which is gives me that 7 minus 8, y is minus 1. We assumed that x is positive, y is negative. The solution that we got is satisfying that criteria as well, isn't it? X is positive, y is indeed negative, right? So this solution is acceptable. This is the first solution that we get. Now let's test for this final fourth case. X is negative, y is positive, which means mod x is minus of x, whereas mod of y is y. So then x plus y equals 8 because mod y is y, but minus x plus y equals 6 because x is negative. Again, we have two equations, add them, x cancels, 2y is 14, so y is 7, and x is 8 minus y, so x is 1. Both x and y come to be positive, but we assume that x needs to be negative. So our assumption based on which we frame these equations is not being satisfied. So this solution has to be rejected. Point to be noted. You break the modulus based on the sign of the input. You assumed that the input are in this way positive and negative. You assume that x is negative, y is positive. You frame the equations based on that assumption and then you solve the equations. The values that you got did not satisfy the original assumption. Hence, it's an invalid solution. Right? This is how typically you solve equations related to modulus. Right? Break down the modulus based on its the sign of its input and then solve them further, and then whatever solution you're getting, you need to back check that whether your obtained values do satisfy the initial assumption or not, because if they do not, then that solution is invalid, right? So therefore option C is a trap option if you do not follow this logic, right? That okay, I'm getting the solution from the third and the fourth one, but remember, in the fourth case your assumption is not being actually satisfied. So therefore only one solution is actually valid. All right, so this helps us to understand the basics of modulus, this question. Let's build further. There is a lot of things to see and how things are handled. I have also brought some mixed questions like this one. Second problem, let's see. If x and y are integers, so that 5x plus 6y equals 99, then what is the least possible value of the modulus of 3x plus 2y? So some overlapping concepts of linear equations are also there that I have brought over here in this problem. Let's see. We know how to figure out or how to define the different integer solutions of a linear equation. We have done this many times in the sessions on Diophantine equations, right? So let's find the first solution by hidden trial of this linear equation 5x plus 6y is 99. And then let's generalize the solutions of this linear equation, because this question is all about this integer constraint. X and y are integers, right? So can I say that let's say 6y is 99 minus 5x. So I'm trying to find that what values of x should I put so that 99 minus 5x becomes a multiple of 6. So if I put x as 1, if I put x as 0, 99 is not a multiple of 6. If I put x as 1, 99 minus 5, which is 94, is not a multiple of 6. If I put x as 2, 99 minus 10 is 89, it's odd. So not even a multiple of 2. If I put x as 3, 99 minus 15 will be 84. That is what will work, right? So the first solution that I got is by putting x as 3, isn't it? And 99 minus 5 into 3, 15 is 84, is the value of 6y. So what is the value of y? 14. 14 into 6 is 84. So my first solution by hidden trial is 3 comma 14. Now the objective of the question is quite different. We have to find the least possible value of 3x plus 2y mod. Now the point is that x and y are to be defined using the solutions of the linear equation, which are integers. So what are the general values of x and y which will satisfy? We know that now the values of x and y will interchange will basically change, so that the value of x changes in terms of the multiples of the quotient of y, which is 6. So it will, let's say, keep on increasing by 6, 3 plus 6 plus 6 and so on, and y, values of y will keep on decreasing by the coefficient of x, which is 5. So in general the solutions are 3 plus 6k, coefficient of y is 6, and y 14 minus 5k. So you can see that 5 into the value of x, which is I have taken as 3 plus 6k, plus 6 into the value of y, which I have taken as 14 minus 5k, this will always add up to 99 regardless of the value of k, because 5 into 6 30k, 6 into 5 30k cancels out, and 5 into 3 15 plus 6 into 14 84 equal to 99 is maintained. Now comes the question, I have to minimize, I have to find the least possible value of this expression 3x plus 2y, right? So in place of x and y, we can substitute this, right? So my expression, let's call that as e. That expression e can be defined as in terms of k. So I am not right now not writing the modulus expression. I'm just writing e. The value that I'm trying to minimize is mod e, right? 3x plus 2y becomes thrice of 3 plus 6k plus 6 times of 14 minus 5k, which becomes 3 into 3 9, 3 into 6 18k, and then 6 into 14 84, and minus of uh, 30k, right? 3x plus, sorry, my bad, I think I've written this as 6 by mistake. This was twice of 14 minus 5k, right? Twice of y. So 2 into 14 28, this is 28, and this is minus 10k, which is giving me 9 plus 28 37, and then plus 8k. So I'm trying to minimize the value of the magnitude of this, right? My objective function is 37 plus 8k, the magnitude of that. Now we know that a modulus, the value of the modulus function is never negative. It is at the minimum 0, right? So for mod e to be minimized, I would want e to become equal to 0, right? Now the challenge, however, is that if I put e as 0 in order for this expression to be minimized, I'm getting the value of k to be in as a fraction. It is coming to be minus 37 by 8, which is not an integer. So the point is that this expression can never be exactly equal to 0. But the value which I've got, which is minus 37 by 8, is telling me that, okay, this is the value. You can try to be as close as possible to this value, right? 37 by 8 is 32, so 4, and then 5 by 8, which is 0.625, right? 37 by 8 is minus 4.625, which tells me that the nearest integer value to this expression, which is minus 4.625, would give me the minimization of the expression, right? So at k equal to 5, I expect to minimize the magnitude of e. The value of e comes 37 plus 8 into minus 5. So minus 8 into 5, 40. 37 minus 40 is minus 3. So that mod e is 3, which is the minimum possible value of this expression. And that is the answer. Right? So a linear equation, solutions are integers. Then expression has to be minimized involving the solutions of x and y. That expression is in terms of a parameter, which is, let's say, k. We can define the solutions in terms of a parameter k. That expression has to be minimized. It can never be exactly equal to 0, because if we put it equal to 0, the value of k is coming to be in decimal, which is not allowed, because then x and y will no longer be integers. K needs to be integer. At k equal to exactly minus 4.625, we are getting e to be 0. So the value closest to this, which is minus 5, helps us to minimize the expression, right? All right. Now, next one. Another question on minimization. What is the minimum value of the function fx equals this? A summation of 4 modulus terms. Each input inside the modulus is a linear function of x. Each of these terms, individually, when they become equal to 0, that is the point around which the function changes its definition. So for example, the first term, which is 2x minus 1 mod. So when x is half, 2x minus 1 equals 0, x is half, this term would go to 0. When 3x minus 2 is 0, which means when x is 2 by 3, this term would go to 0. When 4x minus 3 is 0, which means when x is 3 by 4, the third term would go to 0. And likewise, this term goes to 0 when x is 4 by 5. To minimize any modulus function, we should try to make the input as 0, right? Now, the point is that here we're adding 4 modulus. So the 4 modulus are becoming equal to 0 at different values of x, right? Not the same value of x. So there is a kind of a competition amongst the 4 terms that which term should be put to 0 so that the function is minimized. Now, the logic in this question, in these kind of questions, is that whenever you have such kind of summation of modulus terms, and you need to uh, basically put the terms equal to 0, each of them, right? Find the value of x which makes the term go to 0. Now, whichever is the middle term, means there are 4 terms over here. So there are 2 middle terms. There are 4 modulus terms. So whenever the middle term goes to 0, the function is minimized. In the case when there are an even number of terms, there is no single middle term. So you need to check at both the values, both the middle terms, check the value of the function. Whichever is the least among them is the minimum value of the function. So point is, there are 2 middle values, which is 2 by 3. So these numbers are already in the increasing order, half. Then 2 by 3 is larger than that. Then 3 by 4 is further larger, and 4 by 5 is largest. So you need not to check the value of the function at half and 4 by 5 because they are the extreme values. In the middle, there are these 2 values, 2 by 3 and 3 by 4. So if fx is this, you need to find the value of f of 2 by 3 and f of 3 by 4. Whichever is the smaller amongst these two is the least value of the function. So find what is f of 2 by 3, right? So mod of first term 2 into 2 by 3, which is 4 by 3 minus 1, plus the second term goes to 0, right? Because that's the value we are picking. 4x minus 3, so mod of 4 into 2 by 3, which is 8 by 3 minus 3. Lastly, 5 into 2 by 3, 10 by 3 minus 4. Add all of that, you're getting 1 by 3, 4 by 3 minus 1, 1 by 3, 0. 8 by 3 minus 3 is minus 1 by 3. Magnitude of that, 1 by 3. And this is 10 minus 12 minus 2 by 3, magnitude 2 by 3. This is coming to be 4 by 3, which is the first option. So we should not just jump on to mark that answer, because we know that we have to decide between 2 by 3 and 3 by 4. Whichever is the least will be the minimum value, right? F of 3 by 4 is, so 2 into 3 by 4, so 3 by 2 minus 1. Then 3 into 3 by 4, 9 by 4 minus 2. The third term is 0. Fourth term, 5 into 3 by 4, 15 by 4 minus 4. 3 by 2 minus 1 is half. Then this is 9 by 4 minus 2 is 1 by 4. And this is 0. And this is 15 by 4 minus 4 is 15 minus 16 minus 1 by 4. So magnitude 1 by 4. Half 1 by 4, 1 by 4 is 1. 1 is smaller than 4 by 3. So therefore 1 is the minimum value of the function, right? So both these last two questions that I've taken are emphasizing on minimization of the modulus function, right? The idea is if you try to take the input as close as possible to 0, you are able to minimize the function. Let's see next one. Now an inequality I would like to solve regarding modulus, and this inequality is as you can see involving repeated usage of the modulus. So inside we have mod x minus 10, then we subtract 20 and then mod on that, and then again subtract from 40, mod on that is less than 30. How many integer values of x satisfy this inequality? Let's see. Now, so you see the standard result on modulus inequality is that if it is given that mod of x is less than a being a positive number, then the standard solution to that is that x lies from minus a to plus a, right? That is the standard result on modulus, right? For example, if mod x is less than 5, means x lies from minus 5 to plus 5. So this whole modulus is less than 30. Whatever is written inside the outermost modulus, right? Mod x minus 10 minus 20 mod of that minus 40. That whole expression in mod, can I say will lie from minus 30 to plus 30 based on this? So let's start writing that. I think we have to break down the terms, the modulus terms one by one. Mod x minus 10 minus 20, the mod of that, and then further minus 40. This whole thing was inside the modulus less than 30. So this whole expression inside the modulus is in the range of minus to plus 30, right? Now we can take this 40 on both sides. Basically, I'm dealing with a double-sided inequality, right? So on both the sides, I'm adding 40 in the next step. So mod x minus 10 minus 20 mod 40 goes on either side. So 40 minus 30. So this is more than 40 minus 30, which is 10, and this is less than of 40 plus 30, which is 70. So this lies from 10 to 70. Now let me discuss what is the standard result of the inequality. Mod x lies in the range of, let's say, p to q. For example, the way we have mod of something is lying in the range of 10 to 70. So if mod x lies from p to q, p and q both are positive numbers, remember, only then this result holds valid. So there are two solutions to this. Either x lies from minus q to minus p, or x lies from p to q, right? If mod x lies, let's say, from 1 to 2, if mod x lies from 1 to 2, let's say, then x lies either from minus 2 to minus 1 or 1 to 2, right? That's what we have to apply over here next. So let's do that. So there are two solutions further. Either mod x minus 10 minus 20, this whole thing was inside the modulus, it will lie from minus 70 to minus 10, or it will lie from 10 to 70. So mod x minus 10 minus 20 lies from 10 to 70. So we are solving these two inequalities now. Let's further process that. This one tells us that mod x minus 10 is more than of 20 minus 70, which is minus 50, and less than of 20 minus 10, which is 10. Or this one tells us that x minus 10 mod of x minus 10 minus 20. So adding 20 on both the sides. Just 1 second. So this one is that mod of x minus 10. So adding 20 on both the sides, this lies from 20 plus 10, which is 30, up to 20 plus 70, which is 90. Right. Now mod of this one, mod of x minus 10 greater than minus 50. Mod is never negative, right? Mod is never negative. So this is as good as there is no constraint on the lower side, right? The only constraint is therefore from the upper side. Mod of x minus 10 is less than 10. So this is as good as this inequality. Mod of x minus 10 is less than 10, right? What I'm trying to say, if I'm saying that solve the inequality mod x is more than minus 1, the answer is all real values of x satisfy this inequality. Mod is never negative. So mod x more than minus 1, all real values of x satisfy this. So the lower range, which is minus 50, does not give us any solution. The only solution comes from mod x minus 10 less than 10, which means x minus 10 lies from minus 10 to plus 10, which means finally that x lies from 0 to 20. Since we are counting the integer values of x, we have to count them. You can see the options are the number of integer values of x. So here we get 19 values, because remember x has to be strictly within the range of 0 to 20. So the solutions we get from here are 1, 2, 3, 4 up to 19, right? Let's see what happens from here. Here we'll get further a double-sided inequality, two types, right? As per this result over here, mod of anything lies from p to q, then this is the solution we have. So here either x minus 10 will lie from minus 90 to minus 30, or x minus 10 will lie from simply 30 to 90. So therefore either x is going from, so adding 10 on both the sides, minus 80 to minus 20, or adding here again 10 on both the sides, x lies from 40 to 100. Minus 80 to minus 60, in non-inclusive of the boundary values, we will have 59 solutions. From minus 79, minus 78, all the way up to minus 21 in the last, right? And likewise, we'll have again 59 solutions from here, which is from 41 up to 99. So in total, we have these number of solutions: 19 plus 59 plus 59. 59 59 is 118. 118 plus 19 is 137. Right? So uh, inequalities can also be asked. Inequalities involving modulus, and this question illustrates all the different concepts around inequalities on modulus. Okay, time for the next one. Now, an equation we have. However, this time we don't have the only the linear expressions. We have to comment about the roots of the equation below, which involves mod equal to mod, and the LHS has a quadratic expression, right? And the options are involving 2 roots, 4 roots, and also whether the roots are irrational or rational. All that kind of things are there. So I guess properly we need to solve this equation so that we can identify the nature of the roots, right? How many roots are there and whether they are rational or irrational. Now, whenever you see mod of something equal to mod of something, means mod A equals mod B kind of expression, A and B are any kind of mathematical expression, it simply means the further thing is, the further step that you need to write is either A is B, either A equals B, or A equals the negative of B, right? Because we know that the objective, the function, the modulus function basically removes the negative sign if it exists. So the input can be either equal to each other, or the negative of one can be the negative of the other, right? So therefore we simply have to solve the equation, which is based on the two cases. So either x square plus 2x minus 24, either, so this is case one, this equals this itself, which is x minus 24, or the other case, that x square minus plus 2x minus 24 equals negative of x minus 24, which means 24 minus x. Let's simplify the equation then let's see what happens here. The constant term cancels off. X square plus 2x equals x. So x square plus x is 0. So x into x plus 1 is 0. Very simple equation. X is either 0 or minus 1. And in fact, it is not very hard to check that obviously 0 and minus 1 are satisfying the original equation. Right? At x equal to 0, both LHS RHS are 24. At minus 1, they are 25 each. Right? Likewise, here we will get now a quadratic equation properly. X square, x comes over here, 2x plus x, 3x. And constant term also comes on this side, minus 48 is 0. Okay, x square plus 3x minus 48 is 0. Can we do the splitting of the middle term? 48 needs to be broken down as the product of two factors which differ by 3. 48 can be written as 6 into 8. Difference of factors is 2, but we needed difference of 3. Difference of 3, 12 into 4, 48, 12 minus 4, 8. Very large difference, we need only 3. So this equation does not have integer roots, right? In fact, it does not even have rational roots because the discriminant is not a perfect square. You can see, you can check that the discriminant, because we are not able to do the splitting of the middle term, right? You can also double check discriminant is b square minus 4ac, 3 square 9 minus 4 into minus 48. So plus 4 into 48. 48 into 4 will be 192, 192, 192 to 01, 192 plus 9, 201. So discriminant is not a perfect square. So therefore, two roots are rational, 0 and minus 1. The other two roots, the roots of this equation. First of all, this equation does have roots because discriminant is positive, but they are irrational, right? So option D makes perfect sense. All right. So we know how to solve equations. We also know how to deal with inequalities. We also know how to do the minimization of the modulus function. Right? These are the core ideas, the core concepts based on which questions have been repeatedly asked. Now, time to take a look at few previous year questions from this modulus function. Let's see. So, in how many ways can a pair of integers x and a be chosen such that now we have an equation x square minus 2 mod x plus mod of a minus 2 equals 0. Now, CAT 2020. Many ways to deal with this question. But what do you think? What is the first thing that comes to your mind when we look at this? Isn't it the fact that the term x square minus 2 mod x, it reminds me that I can do the completion of squares on this, isn't it? Whenever you see the quadratic expression, always try to think of the completion of square concept, right? Because what I'm trying to think is that the first expression is a quadratic, the second expression is a modulus, the sum of a quadratic and a modulus is 0. You see, a modulus function is never negative. So whatever this expression is, x square minus 2 mod x has to be negative. Only then they could add up to 0, right? It cannot be that this x square minus 2 mod x is positive. Not possible. And remember, it's a, again, question is having the integer constraint. We are looking for the number of solutions says that x and a are integers. So x square minus, now we don't have x square minus 2x, we have x square minus 2 mod x. So you see, x square is as good as the square of the mod of x, right? The square of mod of x is as good as x square. So what I'm trying to say is that this can be expressed as the square, as the quadratic in terms of mod x. Okay, so x square minus 2 mod x, and I can also call this as mod x square. minus 2 mod x, and I'll do plus 1 to the completion of square. So I'll take this term on the right hand side. So this needs to equal. Now I have added 1 on the LHS. I'll add 1 on the RHS, and this term goes on the right hand side. So minus of mod of a minus 2. So mod x minus 1 the whole square, right, equals 1 minus the mod of a minus 2. Point to be noted that the LHS is greater than or equal to 0 because it is a perfect square, whereas the right hand side is less than or equal to 1, because from 1 we are subtracting a modulus. A modulus is always greater than or equal to 0. So 1 minus something which is greater than or equal to 0 is always less than or equal to 1. How can the two be equal? And remember, the values should be integer, because obviously both sides the values will also be integer as long as x and a are integers. The only thing that can happen is either 0 equal to 0 or 1 equal to 1. There is no other possible way to satisfy both the LHS and the RHS equal to each other, isn't it? RHS is less than or equal to 1. LHS is greater than or equal to 0. So equality can only be achieved at either 0 or 1. So we can have two cases. Case 1, both sides are 0, right? Both sides are equal to 0. So if that is the case, then mod x minus 1 whole square is 0. Mod x minus 1 the whole square is 0, which means that mod x minus 1 is 0, because mod of something is 0, so something is 0. So mod x is therefore 1, which means x is plus or minus 1. And RHS is 0, which means that mod of a minus 2 1 minus mod of a minus 2 equals 0. So mod of a minus 2 equals 1, which means that a minus 2 is either minus 1 or plus 1, the standard result of a equation. If mod x equals a, then x is either plus or minus of a, as long as a is a positive number, right? So what do we get? We get that x is either, we get that x is either a is either 2 minus 1 or 2 plus 1, 1 or 3. X is plus minus 1, a is 1 or 3. X has two value combinations, a has two combinations. In total there are four solutions: minus 1 comma 1, x comma a, minus 1 comma 1, minus 1 comma 3, 1 comma 1, 1 comma 3. We get these four solutions from the case 1. Let's move to case 2. Let's move on to case 2, which means both sides are equal to 1. So then mod x minus 1 the whole square equals 1, which means that mod x minus 1 is either minus 1 or plus 1. Simply taking the square root of a perfect square, mod x minus 1 whole square is 1. So this expression is either minus 1 or 1, which further tells me that mod x is either 0, mod x minus 1 is minus 1, so mod x is 0, or mod x is equal to 1 plus 1, 2, right? Mod x is either 0 or 2. If mod x is 0, then x can only be 0. If mod x is 2, then x can be either minus 2 or plus 2, right? We get these three solutions, isn't it? Now, what's next? Combination of values of a. For RHS to be equal to 1, we should have mod of a minus 2 equal to 0. So that 1 minus this should be 0. So 1 minus 0 is 0, 1. Mod a minus 2 is 0 simply can only happen if a is 2. A has only one value in this case, whereas x has three combinations. So in total, we get three more solutions, which is x comma a either 0 comma 2 or minus 2 comma 2 or 2 comma 2. 4 and 3 total of 7 solutions we have. Very beautifully designed problem. Completion of square was the first thought that should come to your mind when looking at a quadratic expression involving the modulus. Sum of a modulus and a quadratic expression are equal to 0. So there's a very small range of values that can make this happen, right? So only two cases, they can be either 0 or 1. In total, analyzing gives us total of 7 solutions. Okay, time for the last question of today's session. CAT 2021. Let's see. Again, very brilliant question. Let's see how can we do this. If R is a constant such that this modulus of a quadratic expression equals R is a constant. Remember, this time he's not saying R is an integer. However, all the options are integers. Mod of x square minus 4x minus 13 equal to 0 has exactly 3 distinct real roots. What's the value of R? 3 distinct real roots. So the base concept, again, I have said this already. If mod of anything is, if mod of x is a, right? If mod of anything equals a constant, then either x is either equal to a or equal to negative of a, as long as a is positive. Remember, this does not hold true if a is negative. For example, if mod of x equals minus 1, then we don't say x is either minus 1 or minus of minus 1 plus 1. That is wrong. This has no solution, right? This has no solution. Mod x is never negative. So just applying that basic idea once again, we can start off like this, that this whole expression equals R. First of all, let's do the completion of squares on the x quadratic inside of the modulus. X minus 2 the whole square, because we see 4x, so we'll write x minus 2 the whole square. X square minus 4x plus 4 and then minus 17. So this is the modulus thing equals R, right? So this needs to have 3 real roots. So we need to ensure it has 3 roots. Let's see how we can ensure that. So x minus 2 the square minus 17. Remember, R has to be positive, right? We can clearly say that this equation will only have solution if R is greater than or equal to 0. So this either equals minus R or plus R, which means that x minus 2 the square is either 17 minus R or 17 plus R, which means that x, so each of the equations is a quadratic equation, right? So when we'll take the square root on both the sides, right, we'll get plus minus sign, isn't it? For example, x square is 1, so x is plus minus 1. Now, what is, so we are expecting to get 4 solutions, isn't it? Because 2 solutions from each plus minus plus minus. But the equation is saying it should have 3 roots. How can that happen? How can that happen? Plus minus of a number is actually only one value. So the only way this can happen is if that number is 0. Plus minus 0 is only one number. It's not 2 different numbers. I hope you're getting what I'm trying to say. What I'm saying is x minus 2 is from the first equation either plus or the negative or the square root of 17 minus R, and the other solution is plus or minus of the square root of 17 plus R. This will definitely give us 2 different solutions because R is positive. So 17 plus R is a definitely positive number. So plus minus of a square root of a positive number, we get 2 solutions from here. This can also give us two solutions. Let's say R is 1. So it will give us plus minus 4, square root of 16, 2 solutions. But if the input inside the square root is 0, then there's only one solution to be had. So when this expression becomes 0, which means that when r is 17, then this will give us only one solution, which is x equals 2, because x minus 2 will equal to 0, right? Hence 17 is the required value. Brilliant. So these are all the concepts, and you can see the different questions that have been asked, and also some expected questions, right? So this was our session on modulus. Again, very important concept. Questions have been asked and will be asked, right? So thank you so much for joining in. I hope to see you very soon with the next session on algebra. Stay in touch, and let me know any doubts, any queries on the chat box, right? We'll soon meet with the next session. Thank you so much, and stay connected. Thank you. Thank you all.